solving algorithmic tasks on HackerRank. I picked this platform specifically because I solved there some tasks many years ago, and it's kind of cool to me. I like how it looks, I like how it feels to solve them, and yeah, my first stream was a bit unsuccessful because I didn't announce it, and I also didn't set the Twitch setting to save the video, so this time I hope it will be better and I will be able to upload it to YouTube later on. So yeah, the idea is that depending on my personal opinion, I pick the task. It may be affected if somebody suggests me something. Today on the Reddit, one person was mentioning that it's cool to use some standard library algorithms during the solution. So if they will be applicable, I will try to do that. But in general, I think these tasks here are not targeted to apply some standard algorithms. Well, depends, of course, but you never know in advance what should you use in each particular case. So I have sorted them out by several parameters. So we will not take easy ones. It's medium and hard. And about subdomains, it's a good question. What's better to use? Depends on personal feelings of each person. Yeah. Probably I can try to do something for search. So yeah. Red nightshirt as path, cut the tree. Do you need to cut the trees here? I guess it's some kind of binary tree. Yeah, it seems like a binary tree. So 50 points score for this one. This is like not the biggest one, but yeah, there are sometimes ones for 25 points. So I guess this indicates also a bit of the difficulty of this particular task. I also have some points saved up, so if something goes wrong and some test cases, to open it to reveal, and this might help. But in general, the approach will be that we try to solve them from scratch. We'll not look at discussions or whatever. I may Google some stuff which may be useful here if we need to remember the syntax of some standard library interface or function or whatever. Or another example is to look at Stack Overflow for some basic thing which doesn't really require to write it again, because there are plenty of samples which are nice to reuse. But let's see if we need them. So what's this task about? We have nodes and edges between them. Okay, so we can cut one of the edges and we calculate subtrees in this case. And we need to know which edge we should cut in order to have minimal difference of the sums. Uh, is this about sum? Yeah, it's about sum. Sum is just an addition of all nodes in this subtree. Yeah, okay. So example is pretty understandable. I guess we can try to do that. The first thing that comes to my mind that yeah, you can probably start from the child nodes and go to the left side. Well, this tree may have different lengths, but in any case, you can try to start with children, and then you don't need to sum the whole tree. You need to just add the parent, and then get. Yeah, so basically, each iteration could be that you get a parent and you add two subtrees. So this may be not the single node, but the whole subtree, which you have calculated in advance in order to get the sum. So what this may mean, that we can probably build a different tree which will get the sums inside these nodes. So this, for example, may mean that this node may become 4 plus 5 plus 3. It's 9 plus 3, 12. Which will mean that if we cut this edge, yeah, it lags a bit, but if we cut edge number 2, we can basically reuse this sum. Yeah, we don't need to calculate all the whole subtree again and again. But that's my first impression. Let's see how it goes. If we can fit the timeouts, because sometimes in the tasks under medium and hard, it's not that hard to solve the task. It may be hard to optimize it and to get some solution which fits the time allowed for this task to run, for the test cases to run. All right, so interesting. Is this binary tree or not binary? Undirected tree. Can it be some weird tree with some more complicated structure? That's a good question. They call it a graph. So if they call it a graph, this actually gives you an ability to do something fishy. Okay. So the input is data there. The values basically of the nodes and edges. Okay. So we get a tree which is basically defined as graph. What do they have in the example? In the example, they have binary tree. Can we rely on that? Yeah, that's interesting. The given tree is always rooted at vertex 1. Yeah, okay. Probably it's in some constraints. Interesting. That would be great to check first what task are we solving, because I see the difference between, well, you understood already, between the description and the examples. Because if we have not a binary tree, well, does it make that much difference? Let's see. First of all, the difference would be for each cutted edge, the difference would be the whole sum of the tree minus the sum of one of subtrees, and one of the subtrees could be calculated the way I tried to describe earlier. Okay, let's try to code something, but let's get it started, because I guess even in case we have some connections different from binary tree, it should not matter that much. We can still sum all of them. So in case, yeah, and we also know that the root is the first node that is given to us. They explicitly tell us this. So root, will it be integer or no? It will be our tree node type, which we will define just now. So let's make it struct, because why not? I don't think we care right now about some private or public access, so we can just make the members and use them straight away. And as usually, tree nodes should have the value, because each node is different. It's like the weight. Let's call it actually the weight. And we probably want to keep a vector. If we knew that it's a binary tree, we would probably either use pair or use just two separate fields like left and right. But here, since we don't have this, probably it's given to us implicitly, but anyways, it shouldn't hurt to use vector here. And inside this vector, we need to have let's give it the pointer to the different node. Okay. I'm streaming from my laptop, that's why it probably lags a bit. I can't say I prepare specifically to make streams, but if that goes well and people are interested, I may start doing that with better hardware at some point. Let's see. So, children, pretty as that. Our dear children, we'll just grab you all and put you together. Alright, so the root node, we may just go ahead and initialize it with data 0 and the empty vector, because yeah, we don't have anything yet. I use here initializer with curly braces, which is like the most common way right now, I think, to initialize structs in C++. Sorry. Then we want to form our tree. Good question if edges are given to us in a way that we can append everything. I think it's not written that it's gonna be like that. So edges are basically indexes as far as I see. So if we have indexes, if they're not sorted, for example, and so on, we may be in a situation that we have in process of creation the initial tree something not connected. Like if this was 5, 6 here, we wouldn't be able to connect them all together at once. But we can, what we can do is we can create the vector of this tree nodes, and then just set up the connections afterwards. Yeah, that seems like a decent idea. In this case, I actually don't need to initialize root separately. It will be just the first element in this vector. So let's use the arranged base loop here. Node. So for each node of the data, we will create an element for the vector. They use here using namespace std. Many people say it's a bad practice, but I don't want to change this whole file just to fit the guidelines. So here I use std vector. I probably will just still use std vector, ignoring the fact that I can skip this qualifier. So we need a vector of 3 nodes. They'll always have empty children at first because we will set these relations in the next loop nodes. Simple as that. Okay. So for each node here is an integer reference actually. So we can be more precise here. And in fact, if it's an integer, it doesn't make much sense to use reference. Let's use ImplaceBack to construct the tree node from weight, and weight is node. Will this compile? We can sometimes check that it compiles. ImplaceBack is supposed to call the constructor for the struct. There is no constructor, so I don't remember if it will call the initializer list, and if it will, do we need to specify the empty vector as a second parameter? Yeah, they should have also button compile. This doesn't compile. I'm pretty sure that another way of doing this will compile, but yeah, it should compile. However, it highlights me this. Let's see why. It doesn't like it. Okay. Can actually be related to the fact we don't know which compiler is used here. So what if we are explicit what we in place back? Alright. Scrolled a bit too far. No. Yeah, now it responds to my scrolls again. Good. Okay, this compiles. I know that we are not returning the right answer, that's fine. Okay, now we know that the root, I don't know if we will need it or not, but the root is the nodes at 0 position. Okay, so now we iterate the edges, and each edge is for some reason a vector, not a pair. I have no idea why. They said that this should always be 2 values. Why is it vector? Never mind. Yeah. I said that I like HackerRank. Now I'm not completely sure about it, because some of these code manipulations they do for you are a bit weird. Probably that's because they try to be universal, and they have some kind of language converter for this placeholder code. So you see very often some leftovers from C and so on. Alright. In this case, it's better to use reference, because it's a reference to vector, not a single integer. So since the edge is filled with indexes, and as far as I remember, the indexes are 1 based, not 0 based, and the default data in C++ is 0 based. All containers are 0 based, so indexes start from 0. We will need to first of all, we need to take first element, and it will be integer which says which node is first, and we need to add -1 in order to address the proper index, and then add children and push back. First of all, let's get references to left and right. So it's left, and the right one is the back of this edge vector, because there are basically 2 elements. One is front and one is back. For vector front and back return references again. All right, so the same trick with -1. So now we want to fill left and right with each other. So here we will give the pointer to the right element, and here the other way around. Okay, okay, okay. At some point we need to know the leaves or the edges of this tree, because we, as I mentioned in the beginning, we want to start from them. Yeah, while we are calculating. How can we do that? We will probably need to start from the root and go further forward to the children each time, and finally reach the step where there is no connection back. And yeah, actually, if we know it's a tree, that means that it cannot connect so that we have loop, because it will not be a tree in this case. Yeah, that's probably the part where it's not a graph. And they would say it's a graph if it was like that. I think they don't say that. Undirected tree. Okay. Yeah, that makes it a bit better and a bit easier to deal with. Let's go back to our code. Yeah. I need to scroll in the right window. Yes, I need to scroll in the right window. So we may also think about whether we can figure out the edges at this step, not to iterate again. Actually, that should be possible, because each leaf element should be visited by us only once. Yes, all right. And everything else should have at least 2 occurrences, to the parent and to the child. Yeah. Even if some node has only one child, it will still have connection to the parent. The exception is the root element. If it has single child, then but we can easily exclude root from this. So if we keep track of all indexes, we can we can see the leaves pretty simple. So what can we do here? We can either keep a set of indexes and keep it empty first, and then it sounds a bit complicated. Let's think if we can do that better. So the task is, well, it's needed only for optimization purposes. not to have an extra loop for this, we have so in the first loop we may fill the set with each index, and or if we have a map, then we can track if element has counter 2 or 1, and if it has 1 in the end. Yeah, and we can remove elements from the map if the counter goes to 0. Sorry if it's a bit messy to understand, that's just a thinking process. Try to figure out. When I do, I will show you how it works. Sounds like a plan. Yeah, so I want to use map instead of vector because in the end, well, probably it's not really that efficient if I think about it, because map introduces extra complexity each step when you insert or remove element there, but if I use vector and iterate only once, this vector, then yeah, it could be okay. So let's have the same size of this vector. Actually, this will look pretty similar to the initial data, but it will have the amount of elements there. By the way, for optimization purposes, we can reserve some space because we already know the sizes of these vectors. This sometimes saves quite a lot of time on allocation if the data is really big, because you don't need to dynamically reallocate data when you reserve it in advance. So now we have this number of elements, and it may become a better idea to iterate using the old well-known loop with I equals 0, I is less than data size plus I, yeah, because this success is in a constant time anyways, so it doesn't make much difference, but we don't need a separate counter. This will actually be a bit nicer with ranges because it will give us a way to have a range-based loop with indexes all at once. So here we will also fill this one with a number of elements, and yeah, in the beginning they should all be, oh, we can actually do this not in this loop, but we use some of the vector constructors which take the size as a parameter. Do they have it here in the, yeah, they have something, something. If I remember correctly, there is, yes, here's the one when you have number and the value which you want to fill there. Then we don't need to switch from ranged base loop. I will go back here. Okay. We don't need this because we will not fill it dynamically. We'll just do it at the initialization point. So we will fill it with 2. No, only 1, comma, sorry. Good. So now here we deal with indexes. So this is our left index. Yeah, it will be integer. They should also actually pass size t or something like that instead of integer, but again, I don't want to rewrite the default code. Why size t? Because it's the default type which is used for as an index for vectors, arrays, etc. And you cannot exceed this size. Right index. And when we initialize all that stuff, we can access left and right index and why did I think it should be 2? It should be 0, yes. Because we may have more than 2, yes, that's right. And we will increase and we'll collect the ones, yes, that's better. So we will plus it. Plus this and plus that. So you see what happens here when we meet a pair. That means that each side of it has a connector, and if one of the elements is met in 2 pairs, that means it cannot be a leaf, because leaf is always if we look at the first picture, it's always on the right side and nothing can be there. So in the end we can iterate this num elements vector, and only elements with accumulated value of 1 are the leaves. So okay. Now we are ready to collect these leaves. For that, we iterate through this array. We need indexes for it, so we will use this format of loop. We are not interested in root, so we can start from the first element. And yeah, if it's equal to 1, then it's a leaf. Yeah. Yeah. It could be, we actually could keep not a tree node pointer here, but instead an index, because we always deal with, yeah, we always have the initial vector where we can access the element by index. But, okay, we can do that here. So if we want to have pointers, then we can do it like that. Nodes. Sorry. Scrolling went wrong. All right. What we can also do here, if we iterate anyway, so we can calculate the sum of the whole tree. We could actually do that right here. Should it be integer? Will we fit an integer with a sum? Yeah, actually, we can use here accumulate just to show how it works. Why not? Because accumulate just sums all the elements. Yeah, like that. 3 arguments. What else does it really require? I don't remember. Initializer. The initial value of the sum. Well, I guess it's just 0 in most cases, yeah. I also think std reduce does almost the same thing, but it just does it a bit differently. So it's the sum of all elements, so it's the whole sum of a tree, and our task is to get what exactly the minimum. So to go to the task, I need to go out of this window and scroll. No, happened in the wrong order, but anyways. Okay. Yeah, so we're interested in similar trees. Let's go through this to make sure that we are not missing anything at this point. If we cut H12, as far as I understand, we get 100 and everything else. Everything else in this case is 1,500. So the whole tree is 1,600. Yeah, and we always get this as a sum of these subtrees. Yeah, I get this right, and seems okay. So if we cut this pair, vertex 2 to vertex 5, this is this one, we get 1,200 as a sum of these 3 elements, and everything else. Yeah, okay. Sounds simple enough. So now we have leaves, and we can actually start going from leaves back to the top. In order to do that, what we can do is to go layer by layer, starting from the leaves themselves and then going to the next, to their parents one by one. And we need to keep track that we have visited some of the elements already. And when we go to the parent, we need that the children are already checked. This is not the case when the subtree, I can show you. So for example, if we start with vertex 3 and go to the parent and go from this to the parent, for this one we don't know yet the sum of this, and we cannot continue here. So we always need to know which nodes are already calculated. What's the best way to do that? Let's think. Yeah, what's the best way? Oh, hi. I see there is a question. High-level idea of how to solve this. Yeah, I think I mentioned this already, but that's not hard to recall. So the idea here is that we can start from the leaves of this tree, not this exact tree, but any tree that we got, and then one by one go to the top of each leaf and accumulate the sum, considering we already know the previous one. So for this subtree it would be, we know it's 500, so we can subtract 500 from everything else. Then we know 600, we can do the same. Then we go to this common parent, and we don't need to calculate all subtree, we can just sum 2 child nodes and the value itself. So we don't need to do much extra work, and when we reach the root, we add only one value at each step. Yeah, that's the high-level idea. There are also lower-level ideas that we wanted to efficiently build the tree and try to do some extra work during the same loops which generate the tree. So basically what we did is to build this tree and to fill the children. In this case, when we fill, we don't know exactly who is the children of who, so we kind of build both directions, but when we find leaves, we already know in which direction we should look. So from now on, we need to keep track of the elements we already visited, and to somehow keep track of parents which already have all leaves calculated. What's the best way of doing that? Let's see. Usually it's something like calculation wave by wave. So we have a current wave of leaves, then we get all parents. But yeah, it's a bit more complicated this time. But I believe we can figure out how to do that in the process. Yeah. So each leaf is just its value. So we can already start to track the minimum difference, the result that we will return in the end of this function. Okay. And we can safely set it to sum here because everything should be less than it. It could also be int max because anything will be less than int max. So the way we calculate each difference each time is we take the weight, so that's the value of the remaining tree in this case, and that's the weight of the leaf itself. So we can make it simpler here because we see how it works, and we can multiply it by 2. So current difference is something we need to compare with minimum. Sorry. Yeah, and in this case we just update it. So new minimum difference becomes the current. So that's a very common way of doing this. But that's not all we want to do at this step. We also want to fill the next wave. So probably you can call it, if I call it wave, let's call it wave, why not? And the initial wave is equal to leaves. In order to work with it, we always need 2 vectors. That's why we kind of usually you go through one of them and then just swap the values in the end. So the current wave becomes the one which you filled in advance. So like here we fill the wave while we iterate and then we swap them. During first iteration it's simple because we kind of know that there is only one connection. No. So this code will change because right now I'm thinking only about the last level with leaves, but we need to add additional checks in case it's not the one and in case it's a different iteration already. So it will have an outer loop here. Basically, the outer loop could check, not if, sorry. Could check that our current leaves are not empty. So it's not for, it's while. Which means that we continue to iterate through all elements we have until we reach the root. Yeah, and when we reach root, there is nothing left, and the leaves array will become empty in the end. And here in pseudocode, it will be something like swap wave and leaves. So the one which we fill here will become the leaves, and we will do the same again, but for different elements. Because of that, we probably want to clear wave here. Okay. So when first iteration finishes, we have all parents. If I'm not mistaken, it's something like that, but we can change it later if the syntax is different. Then, when it's the second round, it's basically the same as every next round. And for each leaf, we want to go through its children. Or even better, yeah. Oh, I think I have a good idea how to deal with that. Because at this point, when we access here, basically we don't access child, we access the parent. And we can do more here. So this element, if we take, we'll work with the reference because we know it exists, is a parent. Yeah, it's safe to add current value, current weight, to the parent. Current weight is this one, and after that we can safely remove this child. That could be cool if we could do that fast enough. But we'll see. In fact, if we have really small, well, in the example we have only 2 children, so this sort should be very, very fast. Not sort, find. I can tell you what we want to do here. We want to find the element we're iterating and add its weight to its parent and remove it from the list of children. So, and what we're searching for, yeah, leaf is a pointer, yes. So regular find should work. And we should always find it. Yeah. Otherwise, we have written something wrong if we don't find it. So at this point, I will assume that we are able to find it. And I will not check this. But in real world tasks, you might want to put either assert here or some check for error and do something if you haven't found it. This might very often mean that you have some issue in the algorithm, which might also be the case here, but we'll find out during test cases. Yeah, HackerRank is nice enough to provide test cases. You don't need to write them yourself. All right, so, and then we want to, well, removing from vector is not the most efficient thing to do. Erase. Will they give me a signature? Okay. I don't remember it erases by exactly by iterator. I guess it can erase by iterator. Yeah. So that's exactly what I need. So at this point, what we have done, we have moved the weight from the child to its parent for the next iteration. And during next iteration, yeah, we want to see if our current leaf has only one child, which means it only has parent, and we have already checked all the children. If it has more, that means we haven't visited all children yet, so we will add it to the next wave to check. And wave, we might need to add same elements to the wave, which makes it kind of a good candidate to be not a vector but a set. So we cannot add nodes twice. Yeah, this sounds like not a bad idea, but then we cannot swap. We cannot swap with leaves unless leaves are also kept in a set, which is not a bad idea. Set of pointers or indexes. Oh, good question. Good question was more efficient. I have no answer for now. Now we should still be able to swap them. And set means we cannot have duplicates. And if we insert something twice, it will not affect anything. That's exactly what we want. So if we still have more children than one, that means we don't have we also have remaining child nodes, and we will just we'll just insert them in the wave again, and won't do anything else here at this point. And check on the next step where we might already fill the remaining children. All right. One colleague of mine in the past said he doesn't like continue because it kind of breaks the workflow of this algorithm. So he didn't like to understand that there is some kind of early return here, but I think it makes code look a bit nicer because you don't have too much nesting, so it decreases nesting a lot. You don't need else in many cases like that. Alright, so in case we still have children, do that. Otherwise, take the first one, so it will be the same, yes. Yeah, looks okay to me. Now we want to understand how will look the last one when we meet the root element, because it will not have, yeah, when we reach root element it will not have any parents, so its children size will be 0 at this point. It should be like that. Or well, yeah, it's easier to check it explicitly. If leaf is equal to this element, it doesn't make sense to do anything with this leaf because the sum will be maximum. So we just continue. We don't do anything in this case, and it will probably lead us to yeah. Do we need to insert it again? I don't think so. But if it still has other children, yeah, but we will not insert it here. Other children will insert it again, and we will still we might visit this condition several times in this case. I'm not sure it will work right now, but it seems like we've done something which looks like a solution. Yeah, again, I'm a bit relaxed here because we have these test cases. Your output, oh, okay. Understandable, I need to take absolute value. Because basically we might have we might need to make to calculate difference deducing deducting the other part. Yeah, so I said this left and this is right, and this might be the opposite way around. But if we take absolute value, it doesn't matter anymore in which direction we deduct. Yeah, it says that it works. Should we press submit or not? Good question. Good question. I would do that because why not? We will know straight away if we have either algorithmic or we have many issues. Okay, that's fine. Sigfold, that's interesting. That's something I didn't expect. Is it always like that, or is there something else? Okay, so we crash here. Nice. But we passed 0. Okay. So where can we crash if we access something which doesn't exist? Can it be like that somewhere? Can it be that we have removed something? So this vector exists all the way through the code. So from the point we create these nodes, they should be valid up to the end. The fact that we store pointers, not shared pointers, which could track that something was removed. Well, as I mentioned, that shouldn't matter because the owner is this vector and it's created first and it's destroyed last, so pointers should always point to the right value. Here and in all other cases, that's always the case. What happens when we erase children? And is that possible that we access something which was removed? We insert here the parent. And leave doesn't disappear. It is just not mentioned anymore in the list of its parent children. Well, there are several ways we can go here. First one is simple. I get the test case which fails and just print the output and see at which step we crash. I think I will go that way. Because, yeah, I don't believe we fixed. Let's take the simple one. Compiler message success. What does that mean? What does it mean? What's that? Why success if it failed? Who is crazy here? I remember it was segfault last time, but here it writes success. Which kind of success is that? Okay. I will assume that this is the wrong message here. Let's unlock it. It's not that big. Okay. Let's copy paste it somewhere for the future reference. And I will use it as a custom input right now. Something wrong with selection. I'm not surprised, actually. Oh. Okay, okay. Did I copy it all? I guess so. Yeah, I guess so. Let's select this and paste it here. And we expect the answer. Well, we should crash as far as I understand, but it's 525. Do we get it? Okay, terminate called. Okay. I'm pretty sure that's something really stupid we've done. Oh, I've done, to be precise. So let's put some login here. No. Okay. Before loop. Before. Okay. Wave. So we get some amount of waves probably. Will we? So does it mean it will not show me? No, it will show me some output. No response. Does it mean that it failed earlier than that? I am surprised. Okay. I will even put it here. Because why not? That all sounds really strange. Really, really strange. Yeah, handle might be a good idea. Might be the case here. No, not after semicolon. Sorry. Okay, so we may copy this part. What the heck? I don't believe it can fail before. Is it -1 now? Okay. Invalid argument. But I didn't even call string to integer. That's did I use the right format? Oh, can it be that it's an error in the code they wrote? I already complained about the code they generate. Can it be that they use it here? So call getLine. Can it be I copy pasted it wrong? So it's called several times. The amount of numbers should match, so they I didn't expect I have to debug the code. Do you think it's about but yeah, they had something in the end, but I don't believe that should be the case. Well, I can call it like that. I think they will show me the test case again. Yeah, now the message is also correct. It's called truncated, but I don't think it's what I should add there. I don't think I should add truncated here. Yeah, definitely not. Full input data. Okay, yeah. I understand now what you mean. But copy pasting always worked for me in previous tasks I tried to solve before. So I'm not sure exactly how that can be. Download. Okay, let's try to download it to see if that's any different from what we have. Does it look? Oh, yeah. I think actually I didn't have the full data because copy paste for some reason didn't copy all of it. Or not. But yeah, this time I guess it failed somewhere else. Yeah, so we called the wait. Okay, so that was the right reason. We can remove this weird logs. So we reach this point, we call waves several times, but then at some point we we do something stupid. Oh, no. So probably we can add more steps inside each step to figure out which exact check causes the crash. Yeah, it's most of the time the same since we don't have debugger here. With debugger we could just attach and see exactly the place where it crashes. Is it enough? After race probably, okay. So number 4, and we didn't get number 5. So, well, I said it should always be found. What if it's not? So we have the parent, which doesn't have us as child. Oh, I guess, well, I think I forgot one part here. I forgot to track the visited ones. Yeah. So we should never, ever try to do this with the same leaf element twice. Yeah, when we have passed this check and we know that it's currently a leaf, kind of leaf, we add it to this cache of visited items. Yeah, and if it is already there, then I guess we do nothing. Yeah, if it was visited, we already did all manipulations. Continue. Otherwise, we insert it there. Let's check the result. It seems to be the right result. Okay. I think I was talking about marking visited elements, but forgot to write the code for it. That may happen sometimes. Okay, let's submit again. I hope I will not find out I forgot another step here. Now that's already better, but yeah, that's the worst part here. So time limits. The good question if the example we're testing against is actually that big, or we are stuck in an infinite loop for some reason. Uh, Usually the test cases grow in size by their numbers. So if it's the seventh one that fails, that might actually mean we meet the infinite loop case. Okay. Okay, truncated again means we need to open the file. Well, it's actually big. Yeah, it's actually huge. So it has 100,000 elements. So this actually might be not the case I expected. So looks like the real performance problem here. So we can expect we have lots of items. And in cases like this, it might make sense to start making some assumptions about our input. Like, it's actually binary tree or something like that. And can we do that? Because I think that removing element from the vector is not the most efficient thing to do. Yeah, like this. So what we could try is to... So theoretically, if the number of elements, well, we don't know how many leaves we have in the end, but usually the tree is something which takes logarithmic time to go through the whole of it. So what does it mean to us? Okay. How many? What I'm thinking now about is whether we should start directly with making assumptions and changing code, or do some artificial example which will fail but show us if we can fit the time limit. But in this case, we cannot just skip removing things, because it will break the whole chain and we will not end the algorithm in time. Will not end at all, I think, because it will be an infinite loop. We need to remove stuff. Interesting. So we can try to look at the data if the index is actual. Oh, if we can reach this. They are pretty random, I should say. Yeah. It doesn't seem that they are ordered in any way. Okay. No, it's not what I wanted. So can I copy paste it somehow here? Because don't think it's a good idea to copy such big files. But what I can have some statistics calculated from this code. Like from the beginning, from this loop you can see how many connections, the maximum amount of connections that the leaf can have. Yeah. This is not needed for the AND algorithm, but it will tell me if my assumptions about binary tree are fine. So yeah, I assign 0, and if this one is better than maximum, so the same stuff I did before in other place to get the maximum. We'll just see out it straight here. Unfortunately, we'll need to submit again to get it through the test case 7. Oh, do I not get the debug output? That's not nice. That's not really nice, because I'm not sure I can copy it. Well, let's try. I wonder how it looks like in this window. We can check the last number. No, it actually might work. So they give you this, but they cannot accept it. Okay. So they basically force me to use IDE or my local compiler to check this. But I'm kind of lazy a bit to do that. And especially with the lags I see during the stream, that might be something which requires me to prepare better. But what we can also do is just to go ahead and change it really fast. Like, why not? Each one should have left, right, and probably possibly parent, and we don't know in advance which. Oh, actually, yeah, we don't want in advance. We don't know in advance if it's parent or a child. What if we use set here as well, because it will be faster in removing stuff. I'm not exactly sure if it helps. I think not. Funny they didn't recognize the matching parenthesis. No, I didn't want to remove insert. I wanted to remove parenthesis. Yeah. That's a funny thing. Sometimes it works really fast, sometimes it lags, and I don't see how it really depends on what. We need to take the beginning of the set in this case and dereference it because there is no front member of the set apparently. But if there is one element, we can still get it through begin. And here we don't need to do it like that. We can just erase it by the value. But as I mentioned, I don't think it matters much. Yeah. We even got slower. Okay. Makes sense to undo stuff. So what ideas do we have left? I'm pretty sure that the slowest part is not the initial setup of the tree, but rather the part with iterations. We probably do a bit more iterations than we could because of this case. Yeah. If we are not ready to handle some of the nodes, we just continue, and it's an extra check, and it's insertion, and we might do that really many times. So what would be the best option to not do that? And can there be some shortcuts which can save us quite a bit of time? So the idea is we need to find a minimum sum, and yeah, probably there might be some cases where we know that we can just drop the whole branch somehow. Good question, good question. So this task appeared to be not really that simple. And I need to think if I want to finish it today or delay it for the next time, because it's almost 10 p.m. for me. I will try a bit, like 10 or 15 more minutes. Let's see. If I don't find an answer right now, I will try again later and probably post what can be done here on YouTube or somewhere else. Or I will check the discussions. If for some reason I cannot do that myself. That can always happen, that you don't see some obvious thing to do. So we can try to go to the picture and see if we can figure out something from the picture. The comparison with the last minimum is actually pretty simple, because we know the sum from the beginning, and we can really easily calculate it each step. So this shouldn't be the case. What if we try to start from, I don't know, from root? Can it be better? Nah. In this case, yeah. We don't know the division of we don't know the sum for the subchildren, then so it won't help us. Can we somehow not skip parents? Can we not add them? We can try not to add them to the list, because we already know at this point, that it's not the case. And here we know the size of children. Okay, and then we probably don't need this check, because we'll never get this node. This should optimize it quite a bit. Oh, really? That was it? So this small thing, that we don't insert something in the next wave? Oh, that's that's amazing. This small piece actually did the thing. So I am impressed. To be honest, I didn't expect that it will just pass the test cases. But we managed to do that. So we earned 50 points. We spent 10 points, so I'm in plus 40. I don't know for what I need these points, but that doesn't matter. And thank you. I think I got only one viewer this time, but that's better than zero. Thank you for joining. I remember some people mentioned that they'd rather watch the recording on YouTube. That's probably more comfortable for most of them. Today we'll probably not start anything else because I mentioned that I don't have too much time left. So thank you. And see you next time. I hope I will do something similar because it's actually super motivating to code in this format. That's an interesting thing to do. Thank you and bye bye.